Okay.
All right. Next up, we've got Don Syme from Microsoft Research in Cambridge, England, talking about type-safe, scalable, efficient scripting on .NET and beyond. Don?
Okay. Eric.
Who needs type safety?
Yeah, I know. You were once you were once with us, Eric. You were once. Okay, thanks everyone. A big thanks to Mads because I did the incomprehensible of leaving my power pack for my laptop in the hotel room. So a very quick, I just borrowed Mads' laptop and managed to get everything installed. But if there's any bits of the demo don't work, that I've got a vague excuse in that we did a quick new fresh install onto this machine of some of the latest work that we've been doing. So one of the things I'm trying to achieve with the F# project, as well as doing sort of interesting language research in a more traditional sense, is actually come up with a practical tool which combines type safety and scripting, functional and object-oriented programming, and in particular to look at keeping functional programming as the sort of primary paradigm for programming in the small, but to look at incorporating object-oriented programming for programming in the large in many ways, but also to look at getting functional programming, and in particular sort of type-safe functional programming of the Haskell ML kind, back to its original roots, which actually were, a lot of these languages were invented as sort of type-safe versions of Lisp, which are really trying to capture this sort of, they were developed in a setting of doing sophisticated symbolic scripting, where type safety was crucial because of the sophistication of the manipulations they were trying to perform when doing Lisp and then its successors. So I'm really trying to achieve a combination of scripting, type safety, functional, and OO programming. So today I want to talk a little bit about that. I want to talk about some introductory F# programming. And I'll take you through some F# case studies and then some recent language developments in the language itself. But first of all, I want to talk a little bit about the value of making things work together seamlessly and of achieving not just, say, performance and not just safety and not just interoperability and not just usability, but achieving a combination of results with an implementation of a language feature. And of course, the sample I want to use is something I worked on for about 5 years, and which most of you will be familiar with, and that is .NET Generics. Because what I saw when I started the .NET Generics project was that the challenge, thanks to very good work from the academic community and from many language developers, and from the people at Java with Java Generics, we knew a lot about what programmers would accept in this sort of design space. But the challenge was really, so we sort of knew a lot about usability. We already knew from an academic setting a lot about type safety. But the challenge was to get a combination of these things with this one particular feature. And so, for instance, there are aspects of the design, such as .NET Generics supporting reified type parameters, is sort of crucial around the edges of type software. We have safety through various means. A crucial decision was to incorporate generics into the common language runtime so that the JIT and the NGen could code specialize where needed to make sure we got to hit the performance mark. And an absolutely key part of usability of language features, especially typed language features like this one, is to make sure it's orthogonal and combines with all the other features on the Common Language Runtime in Visual Studio. And I think we did a good enough job on this, such a good job that you, in some ways, sort of, you don't feel any edges to the feature. You look at this list of things: NGen, app domains, debug, reflection, JIT, dynamic load, profiling, editing, continue, serialization, IntelliSense. All of those, with a very marginal exception of some parts of the editing continue story, all of these work together. All these .NET Common Language Runtime features work together with the feature of .NET Generics. And that, of course, was a lot of hard work, but it's essential to do that hard work to deliver features to programmers, which sort of don't inflict pain on programmers. So in the context of F#, I'm trying to merge some of these different, say, 3 different paradigms, functional, imperative, OO. We're looking at what are the role of types in programming. We want types for interoperability. We want types for insurance, but there's a good reason to say we don't want types at all. At least we certainly don't want to write the types. Okay, so there are tensions going on here. And then we've got scripting, optimization, components. There are actually tensions between these as well. Setting up a language to be a scripting language or a component development language. Setting it up for high performance execution or for sort of easy programming. And in F# we're trying to see, well, how can we do in sort of taking a language design which is type inferred and succinct from the starting point, and to sort of, maybe these things aren't as much in tension as we've traditionally thought there have been. So you know the sort of, the story with .NET. So this is a slide I use with this nice convenient space to put a new language, and of course this has occurred to nobody else in the room to put a new language into the .NET framework. So the idea is we take our core design, a language called ML, and if you're not familiar with ML, it doesn't really matter because it looks different enough that we decided to change the name. And it actually feels incredibly different to traditional ML programming. In fact, I would say in a sense that .NET really seems to bring the ML functional programming paradigm, mixed functional imperative paradigm alive and make it really fly as a technique for programming .NET. Okay, so F#'s a .NET language. It aims to combine much of the best of Lisp, ML, Scheme, and Haskell in the context of .NET. I use words like it's a functional programming language, but what that means to me is math-oriented and scalable. In scalable, meaning typed. You know, we know we can't write 30,000, 50,000, 100,000 line untyped code. It's aimed particularly at I'd say inside Microsoft, in terms of the niche, I'd say I'm aiming at advanced scripting and symbolic programming. So we have some advanced symbolic programming of the kind done in, say, the static driver verifier tool, which is a tool written, soon to be ported to F#, but now currently written in a language called OCaml. And this actually is used to verify the software of the device drivers on nearly all the computers in this room. The machine learning and systems analysis kind of work is also a key area of use for F#, and I'll be going through some case studies later. So as a language, it's actually very similar to this language called OCaml, which I just mentioned. It shares a core language with OCaml, but adds lots of extensions and sort of actually in practice feels quite different, partly because of .NET, but partly because of the language extensions we have. Okay. So let's just go through some simple F# code. I'll go through these one by one. Well, so we've got, it's type inferred, so there's the program at the top, and the F# will work out here that the type is data int star int star int. Integer constants are constants of this kind of integer by default. Similarly, we define a square function. It will work out that that's an int to int function, because again, because multiplication is over integer by default. You'll have parentheses. So here we have tuples here on the right. We have a pattern matching tuple, or a tuple of arguments here on the left. We have a pattern matching on the left here. We're binding 3 variables simultaneously to the results of applying this function. You'll notice that there's no parentheses on a function application here. We can have side effects and sequencing. We have a semicolon operator, and we just have the side effects here. And you'll see some larger pieces of code that, for instance, computing the normal to a surface given by a function f. So you'll see these functions as first-class values being passed around here. We've got a function f, and here we compute points on the surface given by f, and little square and compute the normal to the surface by taking the cross product. Okay, local binding and sequencing. Now and then you'll see this operator down here, this pipe operator, and you'll see bits of code like this, where we take an object and we apply operations to it. It's a bit like object-oriented programming, a bit like link-style transformational programming as well. So we're doing filter and converting to an array and so on. Okay, just to mention that if you download the current F# distribution, you'll see all these ins and these double semicolons and the like. Just to mention, these are all now optional, so in the talk you'll see. So yeah, many people have complained about the fact. In fact, this seems to be the first sort of offside syntax for an ML-like language. So this is now whitespace, like in Python, whitespace is Python and Haskell. Whitespace is sensitive, is significant here. Okay.
In what regard?
What's that?
In what regard?
So the standard thing is the offside rule that's used. So you got to think of soccer. Okay. So the idea is this declaration sets a line here, and if you're offside, if you're behind the line, then the referee calls a penalty, and that becomes this declaration has to be terminated for the rest of the code. So basically, yeah, put it to the left, terminates preceding declarations. Yeah. Okay. Okay, so let's switch over to do some sample F# programming. So we've got Visual Studio here. We've got F# Interactive. Don't worry that the font is very small down here, because you won't have to read that at all, because we'll escape the console window soon enough. So we've got script up here. Let's see, we'll make sure we set the white space settings. We'll just do some simple stuff. So the first thing I want to do is, this is Visual Studio 2005 with the F# add-ins. So the first thing I want to do is a little bit of web access. So what I want to do is grab a web page. I've made the font very big to make sure people can see it, so excuse that it's hanging over the edge here, but it does say goo something here. Okay, so this is what you seem to have to do in the .NET platform to grab the HTML from a web page. It's a little bit more than one might hope, but in the end, well, down here you see a big blue gob of HTML coming back. We can actually just tidy that up a bit and put it into a function. I've actually added here, for those interested who've done a bit of .NET programming, that I've added this using line here to make sure we give up the resource. And this is a common example of how constructs that are baked into other languages just become simple idioms in a language with functions, function values. So we take using an object, and then when we get the object, that will then dispose of the object at the end of the scope. So that just makes sure we close the response at the end of this scope here. Okay, so now we can grab a few more web pages. And so we've got the RSS from the New York Times as well.
When you're highlighting that, you are executing.
I'm highlighting and then hitting Alt-Enter, and then that executes it in the session down below. So now so let's switch over to the Windows Forms library. So we'll just do a little bit of make the form visible, set it to be the topmost, set welcome to Redmond at the top. Set the size. Okay, we'll add a few more controls in, and so add a text box control and put a bit of text across here. Okay, and this one here is making a little function out of library bits and pieces, which will show any value on the screen, any value x. Unfortunately, the font sizes are very small. But basically, this says this can take any value, it can take any kind of object and display it on the screen. So for example, we could display a tuple, we could display an array of integers where they've been paired up with their squares. One of the interesting things about F#, as far as, although it's a statically typed language, and it comes from a tradition of what I would call very statically typed languages, sort of no backdoors in languages like Haskell and in ML and OCaml. In the F# is much more dynamically, there's much more dynamic information available. So we can write this sort of generic pretty printing and formatting sort of routines, which actually are right pain to do in strictly and fully statically typed languages. So you can, sort of this generic programming is feasible through the sort of usual sort of reflection games that are done in .NET. Okay, so next thing we'll do is go to the RSS we got from the New York Times and scan it for news titles. So we'll open up some namespaces, open up a document. Okay. Now, this is actually a little, here are the first few headlines off the New York Times RSS feed. So it's the usual sort of thing. Usual sort of news. One thing I want to show here, let's close this one down, is a quick use of a feature we've been adding just recently, where you're able to use pattern matching. And if you look carefully at this line, basically we're saying we take our document and we run two XPath expressions on it, one looking for language nodes and one looking for title nodes, and we bind the results to lang and titles here. So we're sort of building up we've got a very generic piece of data, which is the XML coming in, and we're kind of giving a schema here for what we think it should look like. And we get the language, the lang and the titles, and then we can display those on the screen. So I'll go through that, through this language feature in a little bit more detail towards the end of the talk. And you'll see that's another version of the same sort of data, the titles from the stories.
What is the pipe greater than symbol?
The pipe greater than, I mentioned that is take this value on the left here, this string here that we've created, and pipe it into this function. Okay, so it's again using this use of functions as first-class values is used absolutely everywhere, either to compose functions together or just to make chains of applications of functions. You can think of this in a sense as just dot, right? Take an object, perform an operation on it, but it's very extensible because you can write new operations to go over on the right here. So there's sort of no limit to what you can place on the right. Okay. Okay, the next thing we'll do is take the text from HTML and build a little web crawler by scraping the URLs. A very typical sort of thing. So down here is a big blob of HTML. And we'll define the pattern we want to look for, and we'll grab the URLs. This bit is fairly straightforward, just to stitch various pieces together. So, for instance, we can find out the URLs that are collected off the new Google News page. Now we'll write ourselves a little synchronous crawler. This is the extent of the crawl function here. You can see we're going to crawl a set of strings. Unfortunately, we have to, because we're going to block the GUI thread, we have to do our applications do events and appending the text. But basically, we're going to keep the set of strings that we visited and the URL that we're currently crawling. And if we've reached our crawl limit, or if we've already visited the URL, then just return the same set. Otherwise, do a fold across all the URLs that we collect. A fold is sort of just like an iteration where we're accumulating state along the way, accumulating this set of visited URLs. So we can do our crawl function, clear the text box, and set to crawl synchronously from Google. This sample goes on to show you how to do the asynchronous web crawling as well, because of course you don't want to be blocking. And just to say, it is of course more complex to do the asynchronous version, but not a lot more complex. That's the function to do an asynchronous get of a web page. You'll notice how nice the signature is here. We take a URL to crawl, and then we take a continuation, which will get called when the response comes back. So you'll, of course, if you're doing asynchronous programming, you'll often see this continuation passing style. But it drops out quite easily with this kind of use of first-class functions. So we get a beginner get response, we wait for the end response, we do a bit more work similar to what we did to read the HTML, and then we continue down below. Okay. So now here's just tying that together. Oops. Okay. So just tying that together in the search function for the asynchronous version. Basically, we do a very similar sort of thing, except at each point of the iteration, we spawn off a new thread worker to collect the URLs and then continue on with the iteration. Okay. Okay. So I'm sure that gives you a bit of a feel of how you can acquire data with F#, how you can do some work, how you work with it interactively. I want to go through one of the other nice demos that we have, which is done with the DirectX for managed code. We'll be moving this over to WPF as soon as possible. So we've just been doing that in the last few days.
Don, how many libraries or do you add to the platform for F#? Does it introduce new libraries?
So not many. Yeah. So there.
Repeat the question for these guys.
The question. So it's how many libraries do we add for F#? So the .NET platform is very weak on what we'd call functional data structures. Okay. So it's very weak on immutable sets, immutable maps. So things built out of binary trees where you can't go and mutate the contents. And this is sort of standard part of the course. When I was doing the accumulation across URLs, that's using immutable sets because you don't want to be able to just go and hack on the contents of these values. So it's a little bit weak on those points. So we add libraries for those. We add some idioms, and we add a matrix library and a big num library, and maybe a couple of other things which I'm forgetting about. Some compatibility libraries for OCaml as well, but it's not too much. The samples are in the distribution. They won't use the white space syntax, so they'll be a little bit different, look a little bit different. But they're on the distribution. They're on the web as well. On this, there's a great community website called HubFS, www.hubfs.net. Okay. Okay. So I'll load up this DirectX demo. So often in my demos, I just have these little boxes where I spew some debugging output to if I need to. Okay, so this demo uses a little bit of library helper code, about 400 lines of library helper code, which covers some of the complexity. We've made ourselves a form here it's a self-draw form. So because we want to do the DirectX likes to be in control of the rendering. And we in our little helper library, we made a little class called DirectX Renderer, which that really just captures the bit about setting up the event loop for DirectX and managing the redrawing of the display. Okay, now I just get rid of a couple of these windows here. Okay, now the renderer gives us the ability to hook into the render, the core scene construction. And basically, we can add in new functions to run. This is an event, this standard sort of .NET event that gets fired. And we add in new functions that get executed each time the scene gets rendered. So for instance, we draw some axes and we set up the lights. They're just functions in the helper library. So we can now also set the view matrix. Now you notice that I've marked this data here as mutable, which means we're actually going to change the view as time goes on. So by default, data is not mutable in F#, but you do add that annotation if you want to use mutation. Okay. So now we hook that up with a mouse tracker for the form. And we have our we have our mouse yaw pitch roll on the display. Okay. So what I'm going to do now is add the rendering of a function onto the display. So the function that we're drawing here is actually just this one behind. So it's a function of two variables here. It's also a function of time if we want. And this is the result that we're plotting. And we've got some other parameters. And then we're using a helper function here, which is not a particularly complex one. It just generates the appropriate triangles. This draw surface function to render it on the device. I mean, this is just giving the triangles across the DirectX. So now we can change this function interactively, for example. Or we could make it a function of time. And we can change with some other parameters, such as setting the range. And this one is one that I like quite a lot, this ripple function. Okay, there are some other parameters we can play with here. We can make a denser mesh, or we could set it back to being thinner. Or we could make the mesh irregular. So now it's more dense in the middle here. Okay, that's setting the function back to something stable. Okay, so the next part, you'll see these surface point and surface normal functions that came from the introduction. So I just want to do a little bit of simulation of motion on the surface. And we're going to simulate the motion of hockey pucks on the surface. So this is a data structure, well, one way to define a data structure in F#. A ball is a pair of position and velocity vectors. So we can now define our move ball function here, which for a given time delta and a given surface function basically takes an input ball here. You'll see the inputs being here, ball, position, velocity, and computes a new ball based on the surface, based on projecting the normals of the surface. Okay, we need a little bit of work to draw the ball as a mesh, and we keep an active list of balls. And now we set ourselves a surface, and we can add a ball onto the surface. Okay. Okay, now we might queue up a little train of balls running along here. And we just did that by just spawning up the work items and just adding the balls when the work item starts up. Of course, we could have just added them, but there's some reason why we didn't do that. So we can add a few more of those on. Okay. Thanks to Mad's wonderful laptop, it's actually you can do a lot of computation here. Okay, now we can give it something more challenging to work with.
Don, do you have any support for any type of linear programming?
No. For type, do you mean a type system for linear programming? We can talk about that offline. Yeah. Okay, so there we go. I better get back. Okay, so I hope that gives you a feel for what F# is like. Now I want to talk a little bit about what parts of from the language perspective, what does F# emit? We don't include these features from the OCaml language: modules as values, labeled or default arguments, OCaml style objects, or variants. And there's a bunch of reasons why we don't do that sort of thing.
Thank you.
Is that good that we don't?
Yes,
Yeah.
thank you for throwing those out.
Yes, okay. Okay, good to know. So some are platform limitations, some conflict strongly with .NET objects and other .NET idioms, and maybe for labeled or default arguments we'll add something roughly like VB. Okay, so I sometimes use this video, which was done by someone at Microsoft, to get across why we, quite a lot of people here, feel strongly that functional programming has a lot to offer in the context, especially of programming in the small. So this video is really not meant to be disrespectful to the FXCOP team or to anyone in Microsoft, but because FXCOP is responsible for this amazing, is largely but partly responsible for the high quality of the .NET libraries, which F# totally depends on as a language. But I still want to play it because it does get across some of the sort of insanity that can go on with real world programming. So here's a F# program. So this some people in the product teams use F# to prototype their algorithms, and then they have to translate them across to C# and run the FXCOP rules on them. And we're just going to see what happens to this little program during the transformation into production code. So we'll see that we have, first of all, becomes a struct. The return result of the tuple becomes a struct, and then you have a bit more, static public stuff, and a little bit longer to construct some of the data. Okay, but then FXCOP starts giving some errors, like if you have a struct, you'd better define equals and so on, and get hash code on the struct. And then you're told things like to make some public data private, and then you're told to give more meaningful names than x to the x and y to the values of a point. So they used x coordinate and y coordinate, and in the end this is actually what comes out the other end of the one-line program. So so certainly something is going wrong there.
But Tom, that's what keeps people
Yeah, full employment. Yeah.
Is there automated translation from F# to C#?
It's a .NET language, so it's interoperable. Yeah. So it's.
How did you translate from F# to C#? Automated?
That was a programmer written. That was just showing the equivalent C#, the sort of morally equivalent C# of.
You don't have a translator?
No, we compile to .NET IL. Yeah.
You don't have a source translator?
No, not to C#. No. Okay, so just go through some of the language constructs. So we have let. You've seen this. So the sort of let, although Eric is always bugged by having to write let rec for recursive functions, let in itself does actually cover quite a lot of different concepts in programming. We're binding static values, static functions, local functions. Okay. Talk about functions. I've already kind of mentioned quite a lot about function values and their importance on .NET, on F#. So what you notice is what really literally hundreds of concepts, and certainly in the days before generics, I mean thousands of delegate types. On the whole, I mean there's values to giving names to these things, but on the whole, a lot of the complexity of these hundreds or thousands of delegate types just sort of goes away when you have a unified model of function types. A good test for whether your language has a unified model of function types is whether it's possible to write a usable composition operator in your language, which can unify any sort of, can do a composition of pretty much any two function, what you would consider regular function values. Okay. Okay, and there's a bunch of other things I won't talk about so much, type parameters, generics, but that's all over the place now. Discriminated unions and pattern matching and type inference and recursion as well, sort of isolating out recursive blocks. Okay, so immutability is a default. If you say pi is something, then you go and change it later on. So values can't be changed. I have been told there was a version of Fortran that let you change the value of pi or something. I don't know if anyone knows that, but sorry about that. Similarly with data, the defaults are the data is by default immutable, and you've already seen that you can mark some items as mutable if you really need to. Just to talk a little bit about immutability. Immutability is a highly underrated concept in programming language, in practical programming. I mean, experienced programmers sort of know this, but immutable objects you can give them to your friends and they don't get changed. You can give them to other components, and of course they just come back. You can reason about the properties of these objects in a very strong way. Immutable objects can, for example, be transferred between threads, and immutable objects can be aliased safely. And immutable objects lead in different kinds of optimization opportunities. For instance, less pessimistic copying when returning values from APIs, which goes on a lot in the .NET APIs. Okay. So quickly just let's exit from Okay, quickly some case studies of using F#. One group we've been particularly enjoying working with is homegrown users, the TrueSkill team at Microsoft Research in Cambridge. And this is doing live game ranking algorithms, in particular for the Xbox Live set of games. So a typical F# project architecture will be that people will be looking to use F# for this kind of work: data access, analysis, simulation, and visualization, scripting. They'll have a lot of in this setting. They may have they'll have a lot of data. They have web databases, file-based databases, or SQL Server databases. They'll be looking to use the .NET Framework libraries. They'll be looking maybe to use the C++ engine, maybe some private C# components as well. And maybe also wanting to integrate the use of tools like MATLAB. And in this case, it's actually this combination of components. And they also use toolkits like Alchemy and other libraries a bunch of other libraries as part of their work. Okay, so the machine learning group have what they consider to be the most advanced ranking algorithms in the world. They take it very, very seriously. They think it's a major part of the player experience of Xbox Live, that players get ranked appropriately, and they get ranked. It's not just in a sense like a chess ladder system, but you're also modeling the probabilities, so modeling how accurately you know someone's rank. So it's actually a rank is more of a distribution. And all Xbox, so these guys give F# binaries to, more recently they've been switching to giving F# binaries to product teams who do massive background server-side analysis of the game logs of who played who and who should have what rank. And pretty much, this is now pretty much the standard ranking algorithms being used by Xbox Live. Okay, so the sort of thing they're doing is, say, analyzing 4.2 million Xbox Live user feedbacks. Data's in a database. They adopt this TrueSkill model, and the F# code for this problem was, say, 100 lines long and 3 to 4 hours. And they were quite stunned at the sort of performance they were getting out of this. Yeah.
Why are you stuck on performance? Are you expecting a slower time?
No, I think yeah. So the question was why were they stunned by the performance? I mean, I think when you come to an interactive development environment like this, you just assume that it's interpreted and slow somehow. That's just, if you're doing, I don't know, that's just I guess that's one of the remarkable things about F#, is that the code you're running through the interactive environment is often as fast as C++. I mean, it's the same, roughly as the same performance profile as C#. So you're doing interactive development, but with full-on performance. And of course, it's also the performance of the .NET libraries, which counts. The I/O libraries are just fantastic, for example. Yeah.
Why do you think that the code for F#
Why? Yeah. So usually it's about a factor of 3. So what? Yeah. Sorry. Why do I think the code ends up considerably shorter? So for example, in this case study, a framework for probabilistic inference, it was 2,000 lines down to 400 lines. You end up writing only 1/3 as many classes. The combination of object expressions, the use of tuples, and the use of anonymous functions and a bunch of other things just mean you just don't write anywhere near as many classes as you would in C# coding. And that just makes a lot of things smaller. The type inference certainly means just your whole code just becomes a lot more compact. It's really the immutable data structures. That doesn't necessarily make things smaller, I would say. In fact, often using immutable data structures involves plumbing them around because you can't more than you might. So I would say it's a type inference mostly. Yeah.
What about the development time? That development time, 2 weeks, that's for those 400 lines?
This was a framework, so most of the design is in designing the external API to the classes.
I guess
Yeah.
what I'm getting at is that would the development time have been longer if you were going to do it in C#? Is that what you're telling us?
Certainly, if you asked our users that, they would say that. Would the development time have been longer in C#?
And you don't have input into how?
We've never done. I wouldn't ever claim total. I would never. I'm very careful to only make claims which I can actually substantiate, right? And we've never done a controlled study over end-to-end user development time. And there's lots of other factors that come into that. But I think our users seem to feel that the development time is shorter. So. Okay, so they were happy, this sort of thing. They were pretty keen about the performance, about how short the resulting code was, and actually this was a new F# user. He'd only been doing it maybe for 1 month, 1.5 months, and he certainly seemed to enjoy what he was doing. Okay, I want to talk a little bit about the F# approach to object-oriented programming. How much time have I got? I haven't got a watch. 15 more minutes, that's fine. So first of all, one of the key things, you've noticed that everything is type inferred, and there's been a long-standing body of research about how to incorporate type inference in the presence of subtyping. And I think what we've done here in F# is actually really just a very good compromise, which works extremely well in the context of most of the research in this area has been done in what are called structural type systems, where you're interested in sort of compatibility, a little bit like duck typing, I guess, compatibility happening by magic. .NET has a nominal type system where everything's named, a class is named, interfaces are named, and so on. And type inference in that setting is much, much more tractable, and feels the technique we've used feels like it hits a sweet spot in the design space. We certainly embrace object-oriented programming. We embrace the dot notation, and we permit the full .NET single inheritance model. And it's partly mainly for interoperability and .NET style library design. But it's actually a really nice OO language as well, and we get sort of different classes of users, some who only program in the functional subset, some who only program in OO, and gradually the two paradigms just begin to mix together very nicely. Yeah, and I've already mentioned the classes tend to only get used where really necessary to model important abstract concepts. Just to say, for example, just one small example of this, if you have a nice little bit of functional programming like a record type here, and you start doing a whole lot of functional programming code, you could imagine this being hundreds of lines or 1,000 lines sort of complex algorithms over these data types as well. You can then add augmentations, which give effectively an OO view of the functionality that you've created. So you'll now then be able to call methods on this type, point.create and so on. And that it's important because there's the part of the value in functional programming is the ability, its ability to crack the complexity of algorithms. So we don't want to compromise that. But the OO presentation technique is fantastic for programming in the large. And so, for instance, in the signature, you can actually hide all the functional implementation of this kind of that's hidden in the implementation, and you'll just see the members on the outside. Just to say the full class model is supported, there's a little bit of the syntax. Okay. Just to say, all the code that you write in F# can be immediately accessed from C#, even constructs like discriminated unions. We give part of the F# specification is how they are going to appear from C#. And for example, you can look in the object browser and in the specification as to how they're going to appear. What that does mean is that pattern matching something like this in F# will unfortunately have to become somewhat larger in C# because it just doesn't have pattern matching in the same way. But still you can do it, and that can be crucial, for instance, if some people on a team are writing F# components but the testers don't know F# and they need to exercise the functionality as part of the testing process. Okay, thanks. Okay. So another next case study is on packet mining. So Mads's computer is taking a while to talk to me. Okay, the packet mining problem. And so this is where people in the systems group at Microsoft Research in Cambridge have collected a vast amount of data. 4 terabytes of packet capture. It's just like crazy. I'm not sure exactly what they expect to find in this work. It's sort of they certainly decided that if they're going to get that much data, they need to need some high performance tools to do some analysis over it. So their task is to mine data for performance and usage information, and the initial work that they've done is say 2,000 lines of packet reader and demultiplex library in F#. And again, they knew they could write this in C++ to get the performance, but it just wasn't flexible enough. It just was too painful when the formats changed. This is very boilerplate sort of code. I mean, I wouldn't say this is exciting code, but you notice them sort of modeling the packets that come through. We've got TCP and all the others here, and modeling the sort of decomposed versions of those and the functions to project into the packets and so on. It's sort of drab, but it's also dead simple, and it's efficient and it's succinct, and that's kind of at least what you want from drab code. This is a plot of just as some initial results from their work. They're certainly happy with being able to crack the packets, and this was just a plot of who talks to who around our laboratory. We had a video for this, but unfortunately the resolution wasn't quite good enough. But basically you can see the servers here because they're talking to lots of people. And you can also see that if person A talks to person B, well, person B normally, machine B normally talks back as well. Okay. So I wanted to talk about dynamic and static issues in the concept of in the context of F#. So F# is certainly what I'd say, I'd call it function oriented and statically typed oriented or statically oriented. Okay, so it definitely originates from ML. It's sort of trying to get back to this original goal of ML as being a sophisticated, interactive scripting language. But it's because it's statically typed, we know for sure that this kind of programming can scale to very large programs. Because people have written programs, this big and bigger in ML, and no problem. But it's traditionally been an interactive language, but it's not otherwise been a very dynamic language. In fact, I'd say ML had a extremely rigid typing and no reflection, no runtime type representations, no type rediscovery, by which I mean casting, no dynamic loading, no editing continue, no debugging half the time, sort of no nothing. So like programming in ML felt like it was sort of going to a sort of Spartan existence. So when we look at the dynamic features that people tend to use in the that I tend to use, certainly in the context of F# programming, then we begin to say, well, actually, it is a very sort of dynamic programming paradigm. Certainly not in the full-on dynamic languages sense of duck typing and so on, although you can kind of mimic that in many ways. But we've got many different aspects of dynamic programming in as part of the standard kit. A lot of this, of course, comes from .NET. And I do denote that there are trade-offs here. If you're allowed to arbitrarily mutate the type schema, the internal type schema of your program at runtime, as you can normally do in dynamic languages, where you're not going to be efficient. At least no one's ever proved you can be. And F# gets this. I mean, that's part of what the types are for. Okay, looking ahead at trends in static typing and dynamic techniques. The dynamic techniques I'll leave to the experts. I'd be really interested to know what people would put here. So when I look at trends in static typing, we're not going to throw all of this sort of thing into F# by any means, but it's quite interesting to kind of think how some of them relate to some dynamic techniques. For example, in Haskell, for example, and many other languages, they're looking at basically mechanisms, existential type mechanisms that allow you to sort of rediscover functionality that was previously hidden. And you can see Java wildcards as being in this space. We see in Scala more uniform extensible object models, or Camel more extensible structural models, and a possible move towards statically checked versions of concurrent programming as well. Okay. Okay, I'll skip over this part. Just to say that we do support LINQ with F#, so this is roughly how it looks. You've all seen LINQ. You actually make the quotation, the expression trees explicit. Here there's two syntaxes. This is a Unicode syntax for doing that, but there's another one, ASCII one as well. And that gets run as SQL in the usual LINQ kind of way. And just to mention that we've been looking at similar, here's the other syntax for grabbing expression trees. We've been looking at applications of F#, of sort of LINQ style metaprogramming to running programs on the GPU. So for instance, we can take a quoted program, an expression tree here, and there's the definition of the function that we're quoting, and we can translate that across to a GPU program and run it. Okay, I'll skip this part. Okay, a little bit on performance. We have F# being roughly the same as C#, but C++ doing better on some kinds of micro benchmarks. And so I mentioned these challenges, that F# is a function-oriented multi-paradigm language. It's largely type-inferred, hence succinct, and it's fully optimized, but also gives you many of the advantages of a scripting language. Okay. So just finally to wrap up, I think a big challenge in modern language design is this combination of techniques. And I really hope that not only, of course I've got hope that F# will do very well and acquire many users, but I hope in this talk I've been able to get across that it is possible to combine some of these techniques if you're careful about how you do it, and that actually there may be an awful lot to gain by delivering languages which do give a combination of performance and scripting and dynamic features and all the other good things that will come from .NET. Okay, so could I take any final questions? Yeah.
How do I have to program in F# so that the code is consumable on C#? And how will C#? How do I have to code in F# for the code to be consumable in C#?
You just so the thing you should, everything's consumable. Oh yes. How do I code in F# so it will be consumable by C#?
Yeah, but wait a minute. In C# everything's an object.
That's right.
So if you're doing functional programming, there's no
Well,
objects.
the values and objects that value. You can think of a value as just being an immutable object, right? That's generally the terminology we use. So I mean, of course, F# compiles to .NET and to IL, and so underneath you get objects. When you have strings, you have a string object. When you have a set, you have a set object, and so
For
on.
example,
Yeah.
a lambda expression. A
Yeah.
lambda function.
Yeah. So
How do I see that?
yeah. So a lambda expression will have a type that's defined in the F# library called a fastfunc type, and you'll be able to invoke that from C#, for example. Yeah. Yeah.
I just wanted to make a comment that I feel like we sort of, we're assuming that there's some big schism here between functional programming and object-oriented programming, which I don't really believe exists.
Yeah,
They define functional in the sense of imperative functional, right? Which is really the
Yes.
of ML and
Yeah, absolutely. Yeah.
the-
Yeah.
Really, I mean, object-oriented programming, there's the list extensions with objects, and the big difference is that, as you just mentioned, that it's either you're doing data types and structural data types and pattern matching, or you're doing procedural data types, which are objects,
Yeah.
and
Yeah.
method invocation. But that's a big difference, but they're not incompatible.
Absolutely
And
not.
objects
Yeah.
are really just
Yeah.
collections of functions.
Yeah. Yeah.
So I don't
And also, it frustrates me greatly that the functional programming community, in a sense, haven't engaged more intensely with the object-oriented languages until, well, in a sense, of course, in Java and in C#, that was an example of the people from the functional language community going, working with the object-oriented languages. But there's an awful lot of goodness in object orientation. Of course there is. It's just, it's a primary paradigm by which we use to build software. So there is I don't think there is a tension between these things. I think you're entirely right. Yeah, last question.
Yeah, in F#, if you look at all your licenses and stuff, it's pretty clear that if you go back a few months, you weren't ever really planning to make a product out of it, make it a real market, mainstream product. Are those plans changing?
Well, so it's not ultimately up to me to make. Yeah, so going back a couple of months, there was you were saying there was the appearance that we weren't going to make a mainstream product of that. I mean, my primary concern is to do good research and to inspire Microsoft to do things better and to set a high standard, as high a standard as I can as a researcher for what we deliver as a company. And but there's many goals here, and I mean another interesting goal is that in this kind of forum ideas get shared, and so I think tech transfer by feature envy is one of the best ways of text transfer. You make other people jealous, they go and put it in their language, and that's fantastic. I mean, so yeah, I mean that's my approach to spreading ideas and improving the art of programming. And of course, I'd love it if F# was made a product. I wouldn't deny that, but there's no plans for that at the moment. I mean, we're just pushing ahead as a high quality research language that's really usable in practice. Yeah.
Forever free?
So that was the end of last question, I think. Yeah. So what was the last?
Forever free?
Forever free? Yeah, I'd imagine so. I mean, every language we do Microsoft does is given away for free. Yeah, so of course. I mean, the core language implementation. I think that's absolutely without a doubt.
Are the samples you did today and this updated slideshow
That's right. I'll put these slides up on the web, and the samples are in the distribution. A slightly different form of the samples is in the distribution, and there are lots of other samples there as well. So thanks very much, everyone. I think we've run out of time.